Hello, this is Jens from SecurityValley, and in this video we're gonna talk about ransomware, and we also gonna discuss a possible write-up to one of the SecurityValley Capture the Flag challenges, to more precisely the ransomware attack challenge. But I have thought about splitting the video into major parts. So first of all, a little bit theory. Then I'm going to show you, for those who know how it looks like from the attacker's point of view to perform a ransomware attack. We're going to use therefore my own malware framework, which is the Queen. Show you that in a couple of seconds. And then I show you one possible way how to reveal the possible key that was used for the encryption. Yeah? But this part 2 is everything is related to the challenge. So first of all, we have as usual kind of a attacking or attacker's infrastructure, which is usually you have kind of command line interface or an interface to your command and control server, and you have your malware, your implant, your Trojan, remote access Trojan, yeah, you name it. And in this video, we're gonna infect here this Kali Linux machine that I've set it up so far for the demonstration here, because I wanted to do at least one video without infected Windows device. And then I show you how a possible attacker can encrypt some of your files. So therefore, I will switch over here to my console, and I have pre-compiled here with the build tool from the Queen's framework a payload or an executable, which is in fact the malware that we're going to use for the infection. So with a few parameters here, campaign key, and we want to have an HTTPS kind of beaconing, and we call it here the Netflix cracker. Yeah, why not? So I've also started the command and control server, and I've also started here my command and control, the command line interface for my command and control server. And we see currently Jens has joined, which is me, and waiting here to do some things. So first of all, let's move it here to my second screen. And here for demonstration purposes, let's start the Netflix cracker here. Switch back here to a new tab. And we see immediately as well receive here a call home from the device. And let's enter a session here. And first of all, we want to increase the call home period time. Instead of 45 seconds, let's say to 10. And in the meantime, we can also publish some other commands to please run a command in the shell, and say we want to list the current directory, and let's print the current working directory, and just to have some things in the queue. And then we need to wait a few seconds, and then that's now the malware is now in the last 45 seconds cycle. So that means round about in 35 seconds we should see here a more verbose output, that every 10 seconds we see a call home here. So in the meantime, let's investigate here our demonstration machine a little bit. So think about, you have a folder important maybe on your machine, and I've prepared here 2 demonstration files. And one is a simple text file, and here's some Latin lorem ipsum demonstration or placeholder text inside. And we have also here a sample or a simple PDF file, and we're gonna now wanna do our ransomware attack on exactly this folder here. So as promised, we receive here now a more verbose call home from our infected machine. And I think now it's a good time, because we have seen here important in our current working directory, that we now want to perform a ransomware attack. So therefore, to be honest, I always need to look at my own help. We need two things here, of course. The AES, or we use the AES encryption here with the CBC mode. So first of all, we need some random bytes, and we should start with 32 bytes for the AES key. And then we want to have a 16-byte random key as the initialization vector for the cipher that we spin up in the remote process so far. And maybe we want to save that, or maybe you as an attacker, you want to save those keys for a specific campaign, or generate each one for infected device or machine, whatever. And then we have here a few commands. This is encrypt directory, and this will perform a recursive encryption. And we want to encrypt dir. Then we need to enter the path here, which is home, like dev, then desktop, and important. Then the command expect the 32 bytes AES key, and then the 16-byte initialization vector. So, and now we can publish the command, and then we should wait 6 or 5 seconds to get a message back. And every time we see the plus here, that means the operation was successful. So let's see how our files are now looking. And we see here some heavy gibberish. It doesn't read that anymore. And the same is here for your PDF. And think about all of your personal images, important work or business or private documents. They are all gone for the moment. So, and thankfully for that, or this demonstration here, let's think about that we have maybe paid 1 or 2 or 5, I don't know, Bitcoins. We are so kind as the attacker to decrypt the directory. So therefore, let's enter here the same directory. And then we should use the same AES key and the same initialization vector that we have used, and publish the command, and wait again here to the plus. And then let's see how our files are now looking. And we want to do a reload and to see, just ignore that gibberish here, that at least most of the original content is restored. And the same hopefully goes here for the simple PDF file. So this is how a ransomware attack maybe or can look like from the attacker's point of view. And now let's talk a little bit more about the challenge. So you have seen here, or as usual, I'm logged in here to ctf.securityvalley.org, have set the categories filter to cryptography, and have opened here the ransomware attack. And you see the victim here was was a victim by a ransomware attack, and we have assumed that we have spoken with some other security analysts for the same kind of malware, and they were so smart, or they were so smart to kind of figure out the initialization vector. And so this is just a hint here, and this could lead, I think, quickly to AES. And then you have, I think it's 3 or 4, maybe 5 modes with initialization vectors. So CBC, GCM, and we focus here on CBC. But I think you have maybe quickly could find that out. So let's look at the challenge files here. So I've clicked already on the link here that leads to GitHub, and let me minimize that and open the challenge. And you see you have here a memory dump from the process that was running. So let me quickly spin up the diagram here again. So we have quickly discovered this path here, from attacker, command and control to your ransomware attack. And then for some reasons we were so smart and have super timing and we have done a memory dump or a memory snapshot of the malware process, because we have made it possible to isolate the process or whatever. And we have a few memory pages here. And what we're now gonna do is, we know that we have an initialization vector of 16 bytes. So that could also mean that the key is also 16 bytes or 32 bytes. It is possible. And we wanna now scan the entire memory with 30 byte chunks. You can think about scan everything in the memory dump or in the memory page that we have so far. And we're gonna need to check if that may a possible key that was used for the decryption. And there are a few things that we can do. One thing is that we kind of assume a higher entropy. So think about, let me quickly open here some Vim. This doesn't look really like an AES key that was used here, because the entropy here is super low and it doesn't look very randomly. So another example, even this one here doesn't look really like a random generated AES key. So that can help us to speed up things a little bit. And yeah, please kind of close that. And what we're now gonna do, there are some tools outside which perform exactly those scans for you. But to be honest, for the moment, I've totally forgotten what was the name of the tool, but it doesn't matter, because I want to discuss with you the way how I did it with my simple solve Python script here. So first of all, let's kill the beacon here. And let's minimize that. And keep in mind, we're gonna do exactly this behavior here with Python. So let's gonna read here, make this a little bit more bigger. Come on. And let's open my script and get rid of the sidebar here, which I've used here for solving the challenge. So first of all, this is quite boring, just some imports from the PyCryptodome, which provides a whole Cypher suite. There's implementation for AES, RSA, and everything you need. And then from the SkyP package, from the statistics, I think the entropy. Of course it's quite kind of complicated for a non-mathematical person to quickly implement some entropy algorithms. And for some reasons I've suppressed here every warning that came up, because Skype or Skippy was always throwing some warnings. I don't know what was the reason, so I've quickly suppressed those. And you see I've excuse me, implemented here the test AES CBC, and you maybe in your script you have also test GCM, ECM. ECM doesn't make any sense, but you got it right. And the function here is receiving the data, the key, and the initialization vector. Then we want to open here all the encrypted files, and if you see this file here, let's open with some quick editor. Come on, let's open the terminal here. Quick to the desktop, to the challenge, and if we cat here, you see this is probably some gibberish, but for the reason that this name here is a flag, that should throw your attention. So back to the script. We read here the encrypted file, not that magic, and then we read everything from the current directory which end with page, and we yield here. That means we just return here a generator for each file, and then we can kinda iterate it. So then we have a function here, read byte parts, which receives n for the number of bytes to read, and then the dump, which is the file that we receive here from the read input. and then we set the start index to 0, and then with the seek command, you can think about of moving a pointer or an offset pointer from the file, 1 byte by 1 with a length of 32, to get all possible 32 bytes out of the memory page. Just remember what I've showed here. Think about it. Scan the file with a 30 byte long list here, and scan through the entire file like so. And in the main function here, we have for sure calling the read encrypted file. Then we create simple bytes from the initialization vector, and then for every page file in our current directory, we through here or we print here that we stream from the current file, and then we calling the read byte part 32 and the dump, which is the file itself. And then from the byte array, so in the byte array there are every possible 32 byte combinations from the file that we have read so far. We measure the entropy, and you can adjust and tinkering a little bit around on yourself, but for me it was kind of a good result to check if the entropy is greater than 3.0, and then to try to test the AES CBC and decryption here. So far so good. I would say let's run the script here. And then you see here some nice output, and it's starting here streaming from the memory page 1, and this is every possible 32 byte pattern that which an entropy greater than 3.0, I think so. And I'm thinking about what we can do in the meantime. I think we can, it's worth looking at the Python script again. And interesting that if I move the terminal around, that with the output formatting changes or so. That's interesting. But anyhow, I would prefer here to have kindly a new terminal. So what is worth to talk about is you could also think here about use kind of the concurrency packages in Python to speed up the entire script. And yeah, as I said, to speed up things and use kind of a multi-threading approach here. So back to our script. We have seen here some interesting output that maybe look familiar, and yeah, we have successfully in revealing the file, and to be honest, we should have print out here the AES key that was originally used. But anyhow, our goal was to reveal from a memory dump a possible AES key and then do the decryption. And I would say for this little ransomware, we have successfully find the key. And just for completion, I open up here the diagram, and you see what we have done so far. So this was a good way to recover the files and not failing or falling in the position that we need to pay something. So thank you for watching. Hope you had fun, and I'm thinking about it, maybe post the solution script here, maybe as a gist on Git. But you should now get an idea how to proceed with the challenge here. So thank you for watching, and see you in the next one.